So first thing, let's talk about your exam one status. So the exam one is graded, and I have uploaded grades. I haven't sent an email out about this at all, but I have uploaded grades to your WebAssign gradebook, and I think that's where I'm going to keep your grades, because since that's where your homework grades are anyway, figure it was probably best just to keep all of your grades in the same spot rather than putting some of them on D2L and some of them on WebAssign. This way they'll all be on WebAssign. So the way you kind of have to go kind of a convoluted way to get to the grades on WebAssign, but I want you to try to do that and see if you're successful. But when you go to your WebAssign homepage for the course, you should see grades at the very top. There should be several different drop-down boxes, and at the top there should be, I think it's kind of in a blue box, and it should say grades there. And if you click on grades, there's a drop-down. I think if you just click on grades, it'll come up with a page that says raw. In the middle of the page, it'll say raw scores. And if you just click on raw scores, then your grades should come up and your exam one grade should be in there. Now, there have been a few issues with which section people are enrolled in, and some people in the class are enrolled, unfortunately, several times. And so your name appears in the gradebook a couple of different times. So, check and make sure that you're looking at the right one. And I'm trying to put it in all of them so that way, no matter which one you log into, you'll see your grades one way or another. So try to do that. See if you can find your raw scores, and then find your exam one grade. And so now, and I'll send an email out to that effect sometime during the day today. The other thing that I want you to do is, if you want your graded exam back, then you need to email me to that effect and tell me that you want your graded exam back, and then I will respond to your email with an attachment that is your graded exam. So I may not get to that immediately, so if you email me in the next day or two, it's possible it may be a day or two after that before I get them back to you. I'm still trying to get my calculus test graded also. It's my last class to grade, and so I'm currently working on that one. So I'm trying to get that finished before I start sending exams back. So, so does anybody have any questions about any of that stuff about the grades? Janessa?
Yeah, I do. By chance, did you also add the points from the emails as well?
I did. And so when you see if you get your graded exam back, it will not appear in the WebAssign book at all as 2 extra points, but I did add those in. But when you get your graded exam back, you'll see the +2 on the front of the test. So.
Okay.
Any other questions that anybody's got about the tests?
No.
Everybody's okay?
Yeah.
All right.
Good here.
Okay. Then what today we're going to continue talking about. Okay, so your homework for Chapter 8 was due yesterday. And right now, whether you finish the Chapter 8 homework or not, I need you to move into the Chapter 9 homework and start working on that, because you need to start working on radicals and square roots and simplifying square roots as we start thinking about Exam 2. The window for Exam 2 opens up in a little over 2 weeks from now. So, we're pretty close to, we're within about a week of the review going up for Exam 2, and a decent amount of it. Part of Exam 2 will be on Chapter 8, the last couple of sections of Chapter 8, but the bulk of Exam 2 is going to be out of Chapter 9. And so a lot of stuff with square roots and cube roots and fractions as exponents and things like that. So it's really important that you try to keep up with that homework. I would really strongly advise that you do more than what's just in WebAssign, and try to practice problems out of the textbook, and do that consistently. And come by for help. I've started having a couple of you in this class coming by on a regular basis for help during my online office hours. That's great. I'm thrilled that that's happening. And so now it's especially in the evening, I almost always have a couple of students, mostly from this class, but from other classes too. But always have at least one or two students coming by asking questions about either WebAssign or problems out of the textbook. So, all right. So last time we started talking about simplifying square roots, and that's where we want to continue on today. And I want to just review a little bit about what we've done so far with simplifying square roots and finish up section 9.2 and then move into section 9.3 and get 9.3 and 9.4 done. A lot in section 9.2, probably not as much in 9.3 or 9.4 as there was in 9.2. Now remember then with square roots, with simplifying square roots, what we've talked about, first of all, is we've got these properties that the square root of a times the square root of b is equal to the square root of a times b. In other words, you can take two square roots and multiply them. And there are some restrictions on that, but those restrictions don't apply to us at this point. They will later in the chapter. So right now we're going to dispense with any dealing with the restrictions at all. And that property goes both ways. So that means that if you've got two numbers multiplied together underneath a radical, that you can split that up into two radicals like that as a multiplication problem. So it goes both ways. And the same thing with dividing, that if you have the square root of a divided by the square root of b, that's the square root of a divided by b. And it works the other way also, that if you have a fraction underneath the square root, that you're allowed to break it out like that. Now those properties do not extend over to addition and subtraction, and so let's go ahead and write that out right here, and we'll talk about that later today. That's going to be important to us. But it's not true, in fact, that the square root of a plus the square root of b is equal to the square root of a plus b. That does not work. So I'm going to put a not equals right there. So that property does not extend over. And the same thing the other direction, that if you have the square root of a plus b, you cannot write that as the square root of a plus the square root of b. So these properties of square roots do not extend to addition and subtraction. So I'm going to put a minus sign in there too for subtraction. It doesn't matter whether it's addition or subtraction. This property does not work. So properties for square roots only apply to multiplication and division problems. They do not apply to addition and subtraction problems. And that's going to get to be a big deal for us in class today. So I want to put that out there right now and make sure that you're okay with that. All right. So last time what we were talking about is, we certainly started off looking at just square roots, like square root of 81, where 81 is a perfect square, and wrote that as 9. We also talked about powers of variables, that if you took the square root of x squared, as long as x was positive, and we'll always throw that in there, as long as x is positive, that the square root of x squared was equal to x. And then you can continue on with that the square root of x to the 4th was equal to x squared, and the square root of x to the 6th was equal to x cubed, and so on. And so what's the deal? The powers of the variable, as long as they're even powers, are perfect roots also. So even powers are perfect squares. And so that means that when you have an even power underneath the radical, that you can simplify it and you won't have a radical at the end, right? So the square root of x to the 6th is x cubed. And notice there is no radical left there because you've evaluated the square root. And the other thing is, what is the new power? The new power is always half of the old power, right? So the new power is always half of what was under the radical, under the square root symbol, okay? All right, so then we started putting those kinds of things together. So then we had the square root of 36 a to the 8th, right? If you had two factors underneath the square root, we could evaluate each one of those separately. So that was really the square root of 36 times the square root of a to the 8th, and that would have been 6a to the 4th. So we started talking about problems like that. And then after that, we made the jump, so all that was square roots where the number underneath the square root was a perfect square. And so then we made the jump to problems where the number underneath the square root was not a perfect square, like the square root of 12, for example. And what we decided there was that we could use multiplication to simplify that radical. And there is some confusion here on how you do this, because I've had some questions on this since last week. And I want to make sure that you're clear here that 12, for example, breaks up as two square roots, or as two factors, 4 and 3 and 6 and 2, but you only want to use 4 and 3, right? So this is the one you use, and the reason why you use 4 and 3 is because 4 is a perfect square. You need a perfect square underneath one of the radicals. And so that's the one you want to use. And so then evaluate the square root of 4, and you get 2 times the square root of 3, and that's the simplified version of the square root of 12. If you broke it up as the square root of 2 times the square root of 6, that doesn't do you any good because neither the square root of 2 nor the square root of 6 simplifies. 2 and 6 are not perfect squares, and so that is not a factorization you want to use. Neither 2 or 6 is a perfect square. So basically, don't use that. Don't use that factorization. Only use the one that has a perfect square in it. All right, and that's going to come up repeatedly through all of these problems. So that's why the square root of 40, for example, 40 breaks up several different ways. You could break up 40 as 4 and 10. You could also break up 40 as 5 and 8. But which one do you, and 40 also breaks up as 2 and 20. But which one do you want to use? Well, you want to use 4 and 10 because 4 is a perfect square, and that's the only perfect square in any of those factorizations. So that's the one you want to use. So write that as the square root of 4 times the square root of 10, and then the square root of 4 is 2, and so you have 2 times the square root of 10, like that. Now sometimes you have a number, and that's a 48 right there, a number where there's several factorizations. So like 48 is factors as 2 and 24. 48 also factors as 3 and 16. It also factors as 4 and 12. And finally as 6 and 8. Now notice 2 of those factorizations have a perfect square in it. 3 and 16 and 4 and 12 both. So if you're aware of that, pick the bigger one, the bigger perfect square, in this case 16. Now you can do it the other way, it just takes you an extra step, or an extra step or two. So if you notice that 16 is the bigger one and you use that, that's fine. Break it up as the square root of 16 times 3, which gives you 4 times the square root of 3, right? The square root of 16 is 4. If you didn't see that, then break it up as 4 and 12, that's fine. And that gives you 2 times the square root of 12. And what do? Now you continue to simplify the square root of 12. That's the square root of 4 and the square root of 3. and that would be 2 times the square root of 3. And finally, you get 4 square root of 3 that way also. So you get the same thing that way. It just takes you an extra step or two to get to that spot. So look for perfect squares for these problems. All right. And so then if you have a variable underneath the radical that's not an even power, so let's say you have x to the 7th, you really have the same thing going on here with x to the 7th that you did with 48 and 40. There's several ways to break up x to the 7th. You could break it up as x times x to the 6th. You could break it up as x squared times x to the 5th. You could break it up as x cubed times x to the 4th. And really, that would be it. Whoa. Xavier, you might want to mute yourself. Thank you. And if you have a question, that's fine. But it sounded like you had a candy wrapper in there, Xavier. And, unless you have enough candy to share with everybody in class, then.
Oh, no, I'm just making me some cereal, that's all.
Making some cereal?
Yes, sir.
Well, again, if you don't have enough for everybody in class, then we're, I'm just giving you a hard time. So, okay. So which one of those is the one that we want? Well, we want the one with the biggest even power in it. And so we want, we want x times x to the 6th, like that. Because that's the biggest even power. So that's the one we use. And we break this up as the square root of x to the 6th times the square root of x. And then remember, even powers are perfect squares. So we can evaluate that square root and we get x cubed times the square root of x. Don't forget, when we're using variables here, we're always assuming, again, that x is greater than or equal to 0, that the variables represent positive numbers at this point. We're not going to look at ones that represent negative numbers. And so that's the simplified version of the square root of x to the 7th is x cubed times the square root of x. So you're always getting the biggest power that's even. So if you have the square root of a to the 29th power, the square root of a to the 29th, biggest even power you can get out of that would be a to the 28th, right? That's the biggest even power less than 29. So that'd be the square root of a to the 28th times a. That would give you 29 a's right there. And then the square root of a to the 28th would be a to the 14th. Remember, you always take half of the power. So you have a to the 14th and then times the square root of a. And remember, right here, we're saying that the square root of a to the 28th and a to the 14th are the same thing. So we're just replacing the square root of a to the 28th with what it's equal to right there. And the square root of a just kind of trails along. Michelle, go ahead.
Okay, so how come we never do anything with the second square root?
Because the second one's not a perfect square, so there's no way to simplify it.
So you only just make sure that you always find one that's a perfect square?
Right. If both of them are perfect squares, then the original number would have been a perfect square also. So you're typically never going to find both factors to be perfect squares. It's always going to be one of them. And if you look at, Michelle, all the way through this, when I started at the bottom of this page, so the square root of 12 was the square root of 4 times the square root of 3. The square root of 3 was the one that was not a perfect square. So I can't simplify that at all. So it just keeps on getting written down over and over again after that. It's the square root of 3. And you're just replacing the one that is a perfect square with what it's equal to. Same thing on this page with the square root of 40. Square root of 10 was not the perfect square. So there's nothing I can do to simplify that. And so I just keep on writing it down over and over again after that because there's no way to break it down any further. Same thing here with the square root of 3 on this one, and so on, right? So same thing with the square root of x right here. Square root of x just keeps on getting written down over and over again. Okay, so that one, yeah, once you've broken off the one that's not a perfect square, then that one just keeps on getting written down from step to step. All right, so now these were all things we talked about last week. So we finished kind of with problems like this. So if we had the square root of 60, a to the fifth, b to the fourth, c to the ninth, let's say. What you're doing there is you're looking at each of those factors separately. And if you wanted to, there's no reason why you couldn't go off to the side and do each one of those separately if you wanted to. Like the square root of 60, again, 60 is one of those numbers that breaks up several different ways, but you only want to use the way that has a perfect square as a factor. And so that would be the square root of 4 times the square root of 15. And so square root of 60 would be 2 times the square root of 15. The square root of a to the fifth, that one, the 5 is not an even power, so you break it up so that you get the biggest even power less than a to the fifth, so that's a to the fourth. The square root of a just trails along. A to the fourth times a is a to the fifth. And so that gives you a squared times the square root of a. Square root of b to the fourth, that one, the power is even. And so that one is one you don't have to break up at all. You know what the square root of that is. That's b squared. And then finally, the square root of c to the ninth. Biggest even power less than 9 that you can get there as a factor would be c to the eighth. So it's the square root of c to the eighth times the square root of c, which would be c to the fourth times the square root of c, like that. So coming over to our problem, if you broke this up, if you didn't do that off to the side like that, if you just broke it up as two radicals like this, then you would do each one of those little the little pieces that I just did off to the side. You'd have a 4 and a 15 for the 60, the a to the fourth and the a for the a to the fifth. The b to the fourth would stay over here with the 4 and the a to the fourth, and there would be no b's in the other radical. And then the c to the ninth, you'd have a c to the eighth and a c, like that. And so you end up with 2a squared, b squared, c to the fourth times the square root of 15ac, like that. So you can see the over and onto the side over here, I've got the 2a squared, b squared, c to the fourth, right? Those are the numbers outside of the radical that you've got over here. And then what's left underneath the radical, this is the square root of 15, the square root of a, and the square root of c. There's no b's left underneath the radical. And so here's my 15ac right here underneath the radical. All right, so we talked about problems like that. And then we kind of finished by starting to talk a little bit about division problems. So, for example, problem number 100 and let's see, problem number 116 in your book. So this is number 116 on page 1034. This is section 9.2 in your book. Problem 116, you have the square root of 108 q to the 10th over 3q squared, like that. Now, one thing I didn't talk too much about last time, because this is towards the very end, is if you have a fraction like this underneath the radical, what you should do first is see if you can simplify the fraction. And sometimes you can and sometimes you can't, but you should definitely do that. In this problem, you can, because I can take 108 and divide it by 3. And 108 divided by 3 is 36. And q to the 10th divided by q squared, you subtract the exponents, and you get q to the 8th. And see, so that fraction simplified, and so do that first if you can. So simplify fraction first, if possible. It may not be possible to simplify, but if it is, then do it. right? So that's what I did there, and I simplified it, and I got 36 q to the 8th underneath the radical. And then that ends up being a perfect square. So you end up with the square root of 36 is 6, and the square root of q to the 8th, you take half of the exponent. Since the exponent's even, I can do that and get 6q to the 4th. And so then you've got it simplified. All right, and like I said, sometimes they simplify, sometimes they really don't simplify. So, you just have to, it depends on the problem as to what you're going to do. So like, for example, on problem number 132.
What do we do with the 3?
Michelle, the 3, I just took 108 and divided it by 3.
Yeah, no, but like, do we put it anywhere to show that's what we did?
No, I mean, I would, technically, what do you, off to the side here, some of you might write it like that, where you'd actually show me that you're canceling a 3 like that, right? And getting a 1 and a 36. But, if you didn't do that, I would have, at this point, I would be assuming that you knew what you were doing and you were dividing it out. That would definitely be okay, just to write it out that way.
Okay.
So, 132, you have the square root of 45 r cubed over s to the 10th. See, now that's a problem where that fraction does not simplify. There's nothing you could do with that fraction at all. That's an s in the denominator, by the way. It's not a 5. Let me make sure that it's clear that that's an s. Sorry, my s's and my 5s just look a lot alike. So there's no way that so the fraction does not simplify. So there's nothing you can do with the fraction. But what you can do then is you split it up into 2 square roots. And you write it as the square root of 45 r cubed in the top and the square root of s to the 10th in the bottom, like that. And then simplify each radical. So then simplify each radical. So in the bottom, the s to the 10th, the square root of s to the 10th, take half of the power there, and you get s to the 5th. See, don't my s's and 5s look a lot different? Very clearly, they look totally different. Let me erase that. Make it a little bit better. Okay, so that's an s to the 5th. In the numerator, I would break that up to 45, and I'd see if 45 had a factor that's a perfect square. And it does have a factor that's a perfect square, and that's 9. So I'd break up 45 as 9 and 5. 45 also breaks up as 3 and 15, but remember 3 and 15 are not perfect squares, and so that is not a factorization you want to use. R to the 3rd power, r cubed, that's an odd power. You want even powers underneath the radical, and so you get the biggest even power you can get from r cubed, and that would be r squared. So you break that radical in the numerator up like that. And so then this is 3r times the square root of 5r over s to the 5th. Like that. See, and this is not, these are problems that a lot of you don't have a lot of experience with at all. And so this doesn't come naturally to you, and I understand that. But because it doesn't come naturally to you, you need to practice this process a lot. And that's why the WebAssign homework is fine. Do the WebAssign homework, but you're going to need more than just the WebAssign homework to get through this, okay? All right. Next thing I want to do is, we're trying to finish up section 9.2, so there's some problems in 9.2 that I wanted to make sure that we were dealing with. So going back to problem 94, you have 8 plus the square root of 96. So that's an addition problem. And notice the 8 does not it doesn't have anything to do with the radical at all there. So all you're doing here is simplifying the square root of 96. The 8 just trails along. So you're looking for a factor of 96 that's a perfect square. There's several of them in this case. The biggest one is 16. It's the square root of 16 times the square root of 6. 16 times 6 is 96. And then 8 plus, and then square root of 16 is 4. And this is 4 times the square root of 6. All right, this is not equal to, let me really emphasize this. This is not equal to 12 times the square root of 6 right there. You can't take the 8 and the 4 and add them together because what's the operation between the 4 and the square root of 6? That's multiplication right there. And remember, order of operation says multiplication comes before addition. And so if you added the 4 and the 8 together, you'd be violating order of operations. And so you can't do that. And so in fact, 8 plus 4 times the square root of 6 would be the simplified version of that first number right there, and you couldn't simplify it any further. I can't take the 8 and the 4 and add them together. The square root of 6 is already simplified as far as it's going to simplify, so there's nothing I can do with that at all. All right, so now talking about these addition and subtraction problems a little bit. Let's say I have 6 plus the square root of 10 over 12. Let's look at a fraction like that. So you have an addition problem there, but we also have a division. We have an addition problem in the numerator, but it's a division problem ultimately. Now the 6 and the 12, again, you cannot cancel those. This is just like back in the last chapter when we looked at something like 6 plus x over 12. And remember, we talked about the idea many times that you cannot divide out terms or parts of terms. You can't divide when you have an addition or subtraction problem because you'd be violating order of operations when you do that. And so 6 plus x over 12 is in simplest form. There's nothing I can do with that. And that's the same with 6 plus square root of 10 over 12. This is simplified. And there's nothing I can do. The square root of 10 does not simplify. And so there's nothing I can do to, because the only factors of 10 are 2 and 5, and 2 and 5 are not perfect squares. So that's a simplified form, and there's nothing I can do with that. All right. Now, what about if I had 6 plus 2x, not 6 plus x, but 6 plus 2x over 12? Now, 6 plus 2x over 12 is not simplified because the numerator factors. I can take out a 2 out of the numerator, right? And I have 2 times 3 plus x divided by 12. And see, now I've got a multiplication problem in the numerator, and I can divide the 2 and the 12 out, and I get 3 plus x over 6. That's the simplified version right there. So it wasn't simplified at the beginning. I couldn't cancel at the beginning either, but what I could do is I could rewrite the numerator as a multiplication problem, and then I could simplify it. Okay, so the same kind of thing holds with square root expressions also. So if I have 6 plus 2 times the square root of 5 over 12, I want you to look at how that's really the same problem as 6 plus 2x over 12, that they're really the exact same situation. Can I cancel the 6 with the 12? No, you can't do that. But what you can do is you can factor a 2 out of the numerator. And so you have 3 plus, I'm taking a 2 out, so you're just left with the square root of 5. And then this is over 12. And now I have a multiplication problem in the numerator. Now I can divide the 2 and the 12 out. And I've got it simplified. 3 plus square root of 5 over 6. So the moral to the story there is, if you have a fraction like this, if you've got a common factor in every piece of the fraction, then you're going to be able to simplify it. But if it's not a common factor in every piece of the fraction, then you can't simplify it at all. So I just wanted to kind of point that out and make sure that you were aware of that situation. All right, the next thing I want to look at, let's see, and please, again, stop me if you have a question about something. Everybody's okay? Any questions at all?
Okay, so question.
Xavier.
So the 6 plus square root of 10 over 12 is pretty much already simplified.
Right.
Correct.
Right.
So that would mean that it would go straight into the 6 plus 2 square root of 5.
No. Square root of 10. See, square root of 10 doesn't simplify at all. If you've got, let me write that down again. You have 6 plus square root of 10 over 12. Square root of 10, the only way to break up square root of 10 is the square root of 2 times the square root of 5. But neither 2 or 5 is a perfect square. And so you can't simplify it. Because these are not perfect squares over here. And so square root of 10 is already simplified. There's nothing you can do to make it simpler because all the factors of 10 are perfect square are not perfect squares. Now, if it had been something that's simplified, so let's say it was 6 plus the square root of 24 over 12. Now there's something you can do because square root of 24 simplifies. Isn't there a factor of 24 that's a perfect square? What is it?
Okay.
How would I break up 24?
6 and 4?
Yep, and not 3 and 8 because 3 and 8 are not perfect squares, but 6 and 4, like you said, Xavier, is exactly how you break it up. And so that would be 2 times the square root of 6, like that. So square root of 24 simplifies, and so you would do that in this problem and break it up as 2 times the square root of 6, right?
Got it. Okay.
And now I can simplify that fraction because there's a 2 in all 3 parts of the fraction, right? There's a 2. There's a 2 in the 6. There's a 2 there, and there's a 2 there. And because there's a 2 in all 3 parts, I can simplify this. I can factor a 2 out of the numerator, and I can divide that 2 with that 12. And so you get 3 plus the square root of 6 over 6, like that. All right, so
Okay.
so simplify the radical, but only simplify the radical if there's a factor that's a perfect square. And so 10 does not break down at all.
Okay. So what would we put if, like, you threw a curveball at us like that?
What curveball have I thrown you here? Which one? So
No.
if
So for like
Okay, look.
6 plus.
if this is your problem right here, and I say simplify that fraction, and I say simplify 6 plus the square root of 10 over 12, or so let's say that the problem looks like this. This is the direction. Simplify, and you have 8 plus the square root of 15 over 12. Well, the square root of 15 does not simplify because 15 just breaks down as 5 and 3, and neither of those is a perfect square. So there's nothing I can do with that. And so what would your answer be? Your answer here would be already simplified.
Okay.
That there's nothing I can do to simplify that. On the other hand, if I say simplify, let's say 3 plus the square root of 18 over 12, well, that one there's something I can do. Right, there's something I can do there because the 18 breaks up. How would I break up the 18?
3 and 6?
Don't use 3 and 6. Remember, you only want to use, I know 3 and 6 is 18, but remember, that's right, Sandra, you use 9 and 2. That's right. You only use factors that are perfect squares. And so 3 and 6 are not perfect squares, so I don't use those. But 9 and 2, 9's a perfect square. Remember, you got to have a perfect square as one of the factors.
Okay, got it.
And so then this would be 3 plus or minus 3 times the square root of 2 over 12, like that. Square root of 9 is 3. And now notice there is a 3 in all three parts of that fraction, right? There's a 3 there, there's a 3 there, and there's a 3 inside that 12. And so that means I can simplify this even more. I can take a 3 out, and I get 1 plus or minus the square root of 2 over 12, like that. I just pull the 3 out of those two terms, and then I can divide the 3 and the 12. The 3 and the 2, or I'm sorry. I divide the 3 and the 12 out, so I have 1 plus or minus the square root of 2 over 4, because I divided the 3 and the 12 out. So, all right. So Xavier, that kind of clarifies things a little bit for you.
Yes, sir.
Okay. Anybody else have a question?
No, but I'm still writing down that example.
So Michelle, is that your way of telling me not to flip the screen?
Yeah, sort of. It's a really good example.
Well, of course it is. I made it up. Of course it's a good example. All right. So Michelle, give me the thumbs up when you're ready for me to flip the screen.
Okay, go ahead.
You sure?
Yeah, I took a picture of it.
Aha, there you go.
I don't want to mess everybody else up.
No, you're good. You're good. And I was going to tell you to, by the way, remember, I think sometimes students tend to forget that not only do I upload the lecture, the recorded version of the lecture, so on YouTube and everything, but then I also just upload the notes to your Google site as well. And so if you ever have a place in your notes that you wanted to fill in, but you didn't really want to look at the whole lecture or skip through the YouTube video to get to it, you could just go to the notes themselves and flip through the pages until you get to the page that you were interested in looking at, which would be a lot faster than going through the YouTube video. So don't forget that I've got these notes posted in 2 different places on your Google site. So one with audio and video, one without audio and video. So, all right. So section 9.3, in particular, we're looking at addition and subtraction of square roots. Addition and subtraction. Now, remember, a few screens ago, I told you that if you had an addition or subtraction problem, like the square root of a plus or minus the square root of b, that you are not allowed to add or subtract underneath the radical, which is true. So that's not equal to the square root of a plus or minus b like that. And it doesn't work the other direction either. Square root of a plus or minus b is not equal to the square root of a plus or minus the square root of b, right? And so in one easy place you could verify that is you could look at a problem like this. Let's say you had the square root of 16 plus 25. Well, if you incorrectly thought that you could break that up as the square root of 16 plus the square root of 25, then that would give you 4 plus 5, or 9, is the answer, right? Because you could take the square root of 16 and the square root of 25. But what happens when you add them together directly, the 16 and the 25 underneath the radical? Then you get the square root of 41, right? And the square root of 41 is not equal to 9, right? If it is a problem where you could do it both ways and it wasn't a big deal which way you did it, then you should get the same answer at the end, and we don't get the same answer here. You are not allowed to break it up as an addition problem, right? This is wrong right here. This is wrong, right? You have to write it and do the addition problem underneath the radical if you can. All right, so now then what does that mean for us, like in a problem like this? So like the square root of 3 plus the square root of 2. Is that equal to the square root of 5? No. The property up above tells us this is not equal to the square root of 5. It's not equal to the square root of 5. And so the square root of 3 plus the square root of 2 is simplified. There's nothing you could do with that expression outside of using a calculator to get a decimal approximation for the square root of 3 and the square root of 2 and adding them together. Outside of doing that, it's a simplified expression. There's nothing you can do with it. It's really tempting when you see square roots like that to add them together, but you can't, and you can't subtract them either. So if that's true, then what's the big deal about addition or subtraction? Well, there is one situation where you can add square roots together, and that's if the square roots are identical. If you have like square roots, notice in this case these are both square roots of 5. If you have like radicals, sometimes those are just referred to as like radicals, then you can add those together. And you just simply add them together just like you would x's or like terms with algebra expressions. 3 times the square root of 5 plus 6 times the square root of 5. You know, you have 3 square roots of 5 and 6 square roots of 5, so that means you've got 9 square roots of 5. Right? You can add them together by just adding the numbers in front. It's exactly like, it's really exactly like 3x plus 6x. Right? None of you question that anymore. When you see 3x plus 6x, you tell me it's 9x. Well, it's exactly the same problem as 3 square root of 5 plus 6 square root of 5. That just gives you 9 square root of 5. So if the radicals are like radicals, then you are allowed to add or subtract. So you can add or subtract like radicals. Now it's allowed. Okay, so if we have let's say we have 10 square root of x minus 11 square root of x. Well, are those like radicals? Yes, they are. They're both square roots of x. And so all I do is look at 10 minus 11. You know, 10 minus 11 is negative 1. And so this would be negative 1 times the square root of x. And so you could write that as negative 1 times the square root of x, or you could just write it as negative square root of x, either way. All right, if you have 8 square root of 7 plus 6 square root of 7 plus square root of 7. Right, those are all square roots of 7. Those are all like radicals. And so as soon as you see like radicals, you know you're allowed to add. And so you have 8 plus 6 plus 1, right? That last square root of 7 has a 1 in front of it. And so this is just 8 plus 6 plus 1, which is 15. So this is 15 times the square root of 7. Square root of 7, not 17. 15 times the square root of 7. All right, so if the radicals are like radicals, then you are allowed to add them together. So let's say we have 10 square root of 2a minus 7 square root of 2a plus 15 square root of 2a. Right, those are all square roots of 2a, and so those are like radicals there. And so all you're really doing is looking at 10 minus 7 plus 15, which is 18. And so this would be 18 times the square root of 2a. All right. So let's look at this problem right here. Let's say you have square root of 8 plus the square root of 32. All right, now remember, you cannot add them, right? Square root of 8 plus the square root of 32 is not equal to the square root of 40. So let's emphasize that again. These are not like radicals right there. And so I cannot add those together. right? You can only add together like radicals. So square root of 8 and square root of 32 are not like radicals. I cannot add them. Now, does that mean that this problem is already simplified? Or is this number already simplified? Well, we don't know that yet because the square root of 8 and square root of 32 both simplify themselves individually, right? We can take square root of 8 and we can write that as the square root of 4 times the square root of 2. And the square root of 32, remember you're looking for a factor of 32 that's a perfect square. Square root of 16 times the square root of 2 for the square root of 32. All right, and then square root of 4 is 2 times the square root of 2. Square root of 16 is 4 times the square root of 2. And now notice when you simplify each one of them, now you do have like radicals. And so now at the end, I am able to add them together. After I've simplified each radical, I can, when I write them in that form, now I can add them, and I get 6 times the square root of 2. Right, so sometimes you start off with a problem that does not like radicals, and you end up with a problem where you do have like radicals. All right, this is problem number 184 on page 1043. We're in section 9.3 in your book. This is page 1043, and this is problem number 184. So that's the square root of 45 plus the square root of 80. All right, and these are not like radicals. So I cannot add them. See, and that's where if you don't practice a lot with this, then you don't get used to that idea, and then you make a careless mistake on a test and you say that that's the square root of 125, right? Because you're not, but so that's why you got to practice over and over again this idea of when you can add radicals and when you can't add radicals, so it becomes more natural to you. But what can you do? You can simplify each radical individually. So we do that. Square root of 45, that breaks up. I think we did that one a few minutes ago. That's 9 and 5. Remember, don't use 15 and 3 because 15 and 3 are not perfect squares. 9 is a perfect square. That's the one we want. Square root of 80. 80 breaks up as 16 and 5. And so I could simplify each one of those. The square root of 9 is 3. Square root of 16 is 4. And now I do have like radicals. And obviously the problem was made up so that you ended up with like radicals at the end, and to practice that. So you have 7 times the square root of 5 as your final step there. All right, let's say I have, this is an example. Let's say I have 6 times the square root of 50 minus 8 times the square root of 98. All right. So once again, not like radicals. I can't do anything with those. So I don't try to add them, or in this case, subtract them. Not like radicals. But each one does simplify. All right, so tell me how to break these up. Somebody shout out, how about square root of 50? How do I break up the square root of 50?
25 and 2.
Good, Janessa, that's right. 25 and 2. Very good. And I take my time. I'm going to write it out. Square root of 50 is square root of 25 times 2, square root of 2. The 6 just comes down for the ride. Don't make the 6 disappear. And the next one, the 8, and then the square root of 98. 98 is not a perfect square, but I can break it down. How do I break that one down? Anybody tell me how I can break up the square root of 98?
Would it be
49 times 2.
Charlotte?
49 times 2.
Good, very good. 49 and 2. That's right. And so you can break both of those down. So now look what happens here. The 6 continues to get written down. Remember, the operation here is multiplication, right? It's 6 times the square root of 25. But the square root of 25 is 5. So you have 6 times 5 times the square root of 2 minus 8 times 7 times the square root of 2. Take your time as you go through a problem like this. Just take it one little piece at a time. And now I do take the 6 and the 5 and multiply them, and I get 30 times the square root of 2. And 8 times 7 is 56 times the square root of 2. And then what happens at the end, I made this problem up, obviously, so you ended up with like radicals at the end of the problem. So 30 square root of 2 minus 56 square root of 2 would be negative 26 times the square root of 2. Okay, so hopefully that you're okay with that. Now be really careful and not try to force anything. So let's say I have the square root of 4x minus 3 times the square root of 2x plus 8 times the square root of 16x, like that. Now don't mistake those for being like radicals. None of those are the same radical. Those are not like radicals. There's nothing I can do to add or subtract those. Remember, the square root has to be identical in order for them to be like radicals. And so all I can try to do is simplify each one of those. Now, so I can simplify the square root of 4x. The square root of 4 is 2, right? And so that's 2 times the square root of x. Off to the side here, square root of 4x is the square root of 4 times the square root of x. And so that's how I get 2 times the square root of x. The middle one, there's absolutely nothing I can do with that square root of 2x. 2 is not a perfect square. X is not a perfect square. Nothing I can do to break it up. So that's it. And on the last one, the square root of 16 is 4, right? So that's square root of 16x is the square root of 16 times the square root of x, or 4 times the square root of x. So this is 8 times 4 times the square root of x. And so that gives you 2 square root of x minus 3 square root of 2x plus 32 times the square root of x. Now notice in that problem, at the end, that expression, two terms are like radicals. And because 2 of the terms are like radicals, I can add those together. And the 2 terms that are like radicals are the ones on the outside, right? 2 square root of x and 32 square root of x are like radicals. And I can add those and get 34 square root of x. The square root of 2x term just comes down for the ride. There's nothing else I can do with that. Those are not like radicals at the end. And so that's simplified at the end of the problem. Right, there's nothing else I can do with that. All right, now the author kind of goes just crazy with addition and subtraction. I'm not going to go crazy with addition and subtraction. And so that's about the extent of it, what we would do, and about the extent of what you need to be a decent college algebra student as far as adding and subtracting radicals. So we're not going to go any further than that with addition and subtraction. Now it'll come up again as we go through the rest of the chapter, but just these basic ideas that we've talked about in this section. So today we're going to finish with section 9.4. 9.4, we move on to multiplication specifically with radicals. Multiplication of square roots. And then that will finish up what we're going to do in class today, is to talk about multiplication. So then what do we know then? That if I have the square root of 3 times the square root of 7, that is a problem where I'm allowed to multiply those, right? Remember, multiplication and square roots go together. And so this is the square root of 21, right? Remember that the square root of 3 plus the square root of 7 is not the square root of 10, right? I can't add those together. I can't subtract them, but I can multiply them and get the square root of 21. The square root of, let's say I have the square root of 6 times the square root of 9. Square root of 6 times the square root of 9 is the square root of 54. That's allowed. You can multiply those together. Now the difference between that problem and the one I just did with the square root of 21 is that the 54 does simplify, and I really wasn't paying attention. I guess there wasn't a good example, to be honest with you, because what the square root of 6 times the square root of 9, what should I have done at the beginning? I shouldn't have multiplied them together. I should have written this as square root of 6 times 3, because the square root of 9 is a perfect square. And you should have written it as the square root of 6 times 3. Never write it that way, by the way, because the 3 comes after the radical. Always put, and the 3 is not underneath a radical anymore, right? Because I took the square root of 9 and I replaced it with 3. What do you want to do with that 3? You want to put it in front of the square root of 6. You don't put it at the end because then it gets confusing as to what's underneath the radical. But when you put it in front, then it's very clear what it is. So that was not a particularly good example because you should have just simplified one of the radicals, and I wasn't really paying much attention to that. So, but now if you have the square root of 6 times the square root of 12, this is more the kind of example I was trying to write a second ago. You can multiply these because I can multiply any two square roots, and so you get the square root of 72. Again, there's an exception to that rule that we'll talk about later in the chapter, but that the exception doesn't come up until we get later in the chapter. All right, so the square root of 6 times the square root of 12 is the square root of 72. Square root of 72 does simplify. I can break it up, and the best way to do that would be to break it up as 36 and 2. And then the square root of 36 is 6, so you end up with 6 times the square root of 2. So square root of 6 times the square root of 12 ultimately is the same thing as 6 times the square root of 2. If you use the calculator and got decimals for both of those, you'd get on your calculator, you'd get the decimal approximations look the same. They certainly would look the same there. All right, the next problem, let's say, and actually this is problem number 238. So this is page 1056, section 9.4, and this is problem number 238. So 238, you have 2 times the square root of 3 in parentheses times 4 times the square root of 6. All right, now this is a multiplication problem, so I'm allowed to multiply. Remember, if it had been 2 square root of 3 plus 4 square root of 6, I can't add those because those are not like radicals, right? So not like radicals cannot add these. That's not what you've got in this problem. You've got a multiplication problem. So this is something you're allowed to multiply out. Now the way we do this, this is technically 2 times the square root of 3, and then times 4 times the square root of 6. And because it's all multiplication, you really don't need the grouping symbols in there at all. So this is 2 times the square root of 3 times 4 times the square root of 6 like that. And you can rearrange those factors in any order you want. We've talked about that numerous times this semester, that with multiplication, it doesn't matter what order you write things in, what order you write the factors in. So I would put the 2 and the 4 next to each other, and the square root of 3 and the square root of 6 next to each other. And so what do I get there? I get 8 times the square root of 18. Now, you didn't have to go through all that pain to do that. You should have just seen, hey, I can do that from the beginning and go straight from the first step to that last step there. And then you're not finished because the square root of 18 simplifies. You can break it up as the square root of 9 times the square root of 2. And so that would give you 8 times 3 times the square root of 2, or finally 24 times the square root of 2. So, I would go straight from that top step to 8 square root of 18 right away. So on this problem, if you had, let's say you had 8 times the square root of, let's say 8 times negative 3 times the square root of, let's say, 10. Then I would just go ahead and think about the fact that it's all multiplication and just multiply the factors that I can multiply together. So the 8 and the negative 3 are factors I can multiply, and I get negative 24. And the square root of 8 times the square root of 10, those are factors I can multiply, and I get the square root of 80. So I would just go right to that step right away, get negative 24 square root of 80. All right, and then simplify the square root of 80. It simplifies as the square root of 16 times the square root of 5, or that's how it breaks up. That's how you break it up. And so you get 4 for the square root of 16 right there. And then 4 times negative 24 would be negative 96 times the square root of 5. And that would be where we'd finish on that problem. All right, let's do something with variables. So hopefully nobody's shouting at all, so I'm assuming that you're kind of following this okay. And in the big scheme of things, this is not hard compared to some things we've done, definitely. All right, so I'm still on page 1056. And I was looking at problem number 254. So this is what looks like a kind of a messy multiplication problem. You have negative 2 times the square root of 7z cubed times 3 times the square root of 14z to the 8th. Like that. And like I said, it looks messy, but this is not a hard problem because it's all multiplication. I'm allowed to multiply these in any order I want. So I take the negative 2 and the 3, and I get negative 6. And I take the 7z cubed and the 14z to the 8th, and I'm going to multiply those together also. The 7 times 14 is 98. Z cubed times z to the 8th is z to the 11th. And so I get the square root of 98z to the 11th when I multiply those. So it's already looking a lot better just by multiplying like that. All right, and then now I can simplify, right? So the square root of 98, well, we did that one a few minutes ago. We saw that 98 broke up as 49 and 2. And then z to the 11th, get the biggest even power for z to the 11th, which is z to the 10th. That still leaves me with a z left over here. And so you get negative 6. The square root of 49 z to the 10th would be 7 z to the 5th. And then the square root of 2z just comes down for the ride. And then finally multiply what you have left, and you get negative 42 z to the 5th times the square root of 2z. And then that's the simplified version of the problem right there. So, take your time, multiply the pieces out that you get there, and then simplify the radical at the end. Again, take your time. Don't try to do too much in one step on a problem like this. All right. Now, what happens when we take a square root and we multiply it by itself, like the square root of 5 times the square root of 5? Well, so it's still a multiplication problem, and so that's the square root of 25, and that's equal to 5. So notice the square root of 5 times the square root of 5 is just 5, right? Because you end up with a 5 squared underneath the radical. So if you had the square root of 7 times the square root of 7, you could really write that as the square root of 7 squared. But what is that going to give you? It's going to give you 7. You know, the square root process and the square process are kind of sort of inverse processes of each other, so it's like they undo each other. Now, they don't undo each other exactly if the numbers are negative, but if the numbers are positive, they kind of undo each other. And so we can take advantage of that if we know that. So the square root of 13 squared, like that, well, that's, you know, if you want to, you could multiply it out. But when you take the square root of a number and then you square it, it's like you're not doing anything at all. And so you're just left with 13.
Okay, question. So what if they're both negative?
That's a really good question. And I don't know if you remember me talking about the fact a few minutes ago that there's some restrictions to multiplication. And that's the restriction, Xavier, is when the numbers are negative, is that you really can't multiply them together in a case like that. Now, that's not something we're ready to talk about yet, but we will be dealing with that. So Xavier's question, you know, I've been talking about this fact that the square root of 2 times the square root of 5 is okay to write that as the square root of 10. Unfortunately, if you have both numbers are negative, like that, you are not allowed to multiply those together. This is not the square root of 36. That's the one place where you're restricted from multiplying them together, is when both numbers are negative like that. And that's not a situation we're ready to deal with yet, because we're not talking about square roots of negative numbers just yet, but we will by the end of the chapter. So we will get to that, and so don't worry about it right now. Now, also be careful. That is not anything to do with this problem. Like if you had the negative of the square root of 5 squared, notice that negative sign is not underneath the radical, so that has nothing to do with it. That's just squaring a negative number. And when you square a negative number, you do get a positive. But that's not the same thing as this situation over here, where you've got a negative number times the square root of a negative number times the square root of a negative number. So we'll talk about how to do that, but that'll be later in the chapter. So later in the chapter, because what we need to do is what have we talked about so far? We've talked about the idea that the square root of negative 4 is not real. We talked about that when we started talking about square roots last time. And all I told you to do with the square root of a negative number is just to write that it was not real right now. Later in the chapter, we'll look at square roots of negative numbers more carefully, and then we'll talk about that situation where you have the square root of negative 4 times the square root of negative 9. So that's an excellent comment, excellent question, but it's something that we'll have to work on later in the chapter. Okay, so we're not quite ready to do that yet. All right, so if you have negative 3 times the square root of 10, and that's squared, so then, excuse me for a second while I let one of my dogs into the room. So, one of my dogs was not letting the other dog into the room, and so he was getting upset. So I'm sorry about that. So you're squaring both of these factors. You know, it's a multiplication problem, so just square each factor separately. So this is negative 3 squared times the square root of 10 squared, right? You just square each factor separately. Because it's multiplication, that's okay. Negative 3 squared is positive 9, and the square root of 10 squared, we've just talked about that is 10, right? And so you end up with 90 as the answer when you're multiplying that out. All right, so you should know that when you square a square root, that you end up with something that doesn't have a square root in it at the end. All right, we have maybe 2 or 3 problems left, and then we're gonna stop for the day. So just bear with me. We've got a couple of problems left, and then we will finish. So continuing to look at multiplication. Let's say we have the square root of 3 times 4 minus the square root of 15, like that. Now, how do you think you're going to multiply this out? Anybody want to guess? How would I multiply something like this? I'm looking for 2 words.
Cross multiply.
You might be meaning the right thing, Michelle, but you're not using the right words. That's for sure. So you in your head, you possibly are doing this problem correctly. Those aren't the words we use for this. There's a property that will allow us to multiply this out. What's the property? Starts with a D.
Distributive property.
There you go, distributive property. Very good. This is the distributive property right here. And so we take the square root of 3 and we multiply it by 4, and we take the square root of 3 and we multiply it by the square root of 15. Now the square root of 3 times 4, well, the 4 is not a square root. So there's nothing I can do there. All I can do is write that as 4 times the square root of 3. But the square root of 3 times the square root of 15, those are both square roots, and so I can multiply those, and I get the square root of 45. And then you simplify the square root of 45. You can break that up as we've done that a couple of times. That very square root 2 or 3 times now today. Break that up as 9 times the square root of 9 times the square root of 5. And so you have 4 square root of 3 minus 3 square root of 5. Those are not like radicals, so don't try to force it and don't try to subtract. There's nothing you can do there. The square roots don't simplify. The square root of 3 and the square root of 5 don't simplify, and so you're finished with that problem. All right. So then let's see. This is actually problem number 276 in this exercise set. You have 3 minus the square root of 7 times 5 minus the square root of 7. So how do you think you'd multiply this out? Anybody have an idea here? I'm looking for 2 words here again also.
Would you do the same distributive method as well?
Well, it is the distributive property. Janessa, it is the distributive property. But a lot of people will use another name in this case.
Well method.
Say it again.
Wait.
Justin, I don't know if I can.
Foil method?
Yeah, it's the FOIL method. That's right. This is just a FOIL method problem. We multiply first, outside, inside, last. Now that's really just the distributive property. I understand that. So whoever said the distributive property is certainly correct, that's what we're using. But the FOIL method a lot of times is a nice way of organizing it here. So the first would be 3 times 5, which would be 15. And if you want to, let me write it out like that. That's 3 times 5. Then the outside 2 is 3 times the square root of 7. The inside 2 would be 5 times the square root of 7. And then the last 2 would be the square root of 7 times the square root of 7. It's the last 2 like that. And so you end up with 15. Notice these radicals are like radicals, and so that would give you negative 8 square root of 7. And then the square root of 7 times the square root of 7 would be the square root of 49, which is 7. Remember, when you multiply a square root by itself like that, you just end up with the number underneath the square root. And so that gives me 22, 15 and 7 minus 8 square root of 7. And then you're finished. And remember, the 22 minus 8, I can't do that. And so I would leave that alone. All right, because the subtraction does not come before multiplication. The multiplication comes first, so I just leave that alone. I don't do 22 minus 8 right there. All right, last problem of the day. This is number 288. Number 288, you have 3 plus the square root of 5 quantity squared like that. Now, one way to do this is just to write this as 3 plus the square root of 5 times 3 plus the square root of 5. Because that's what that square means, is that you're multiplying it by itself. And then you could use the FOIL method there to multiply it out. So 3 times 3 would be 9. Outside 2 would be 3 square root of 5. Inside 2 would be 3 square root of 5. And then the last 2 would be the square root of 5 times the square root of 5, which is 5. Right? You remember the square root of 5 times the square root of 5 is the square root of 25, but that's just equal to 5. And so you have 9 and 5 is 14, and 3 square root of 5 plus 3 square root of 5 is 6 square root of 5, like that. Now there is a shortcut for that kind of multiplication problem that we do want to talk about, but I'll probably not do that until we come back for lecture on Thursday. I think we've done enough as it is. So, all right, so done a lot of problems with radicals. Your homework, and this, again, this is practice. This is what you you do as much of this as you feel like you need to, but the more of these kinds of problems you do, the stronger you're going to be with this going into exam 2. So I really advise doing a lot of these problems. And so I know this is going to look like a lot of problems, 233 through 299, and I would say every other odd would be okay there. If you feel like you need more practice, do every odd. That would be okay. 9.3, not quite as much with 9.3. This is on page 1043. I would recommend 145 through 187. Again, every other odd would be okay there. That's adding radicals and subtracting radicals. 9.2, I think I already assigned those problems. So what I'm going to say with 9.2 is look at problems on 1034. So look at page 1034 and 1035 problems and for review there. All right, you have WebAssign homework on all of this, certainly, so be working on that. Be working through these problems right here. Does anybody have anything they want to ask before we shut it down? Remember that I've posted your exam scores on your WebAssign gradebook. And going back to the very first page here, at the very beginning of class today, on your WebAssign homepage, look for grades at the top. It'll say grades. There'll be other selections there, so you click on grades, and it'll bring you to a sheet that has raw scores. The words raw scores sitting in the middle there. Click on raw scores, and you should be able to see your test grade. Also, don't forget that I replace, and I've talked about this several times now, but I replaced the lowest test grade with your final exam. So if you did not do well on this test, it doesn't have to show up on your average at the end of the semester. You know, I think I've talked about that already, but I think it is worth repeating that if these are your exams, and I have students who do this every semester, where exam 1, let's say that this person made a 45. Oh my gosh, that's not a good grade for exam 1. But let's say they do better on exam 2. Let's say exam 2 is a 68. Still not great, it's a D, but it's still better. Exam 3, this person continues to do better and makes a 74. And then the final exam, the student makes a 70, and let's say that the WebAssign grade was decent but not perfect, and let's say that that was a 70. Okay, so look, this student, even though they made a 45 in the first test, what's going to happen? That 45, I'm going to take it when I do my averages, and I'm going to replace it with this 70 from the final exam right here. And this person's going to make a C in the class. Even though they started off with a 45 and a 68 on the first two exams, they still end up with a C in the class. And notice that the grades that I wrote down were not stellar the rest of the way. They were better, but they weren't just outstanding. So a student who made a 45 in the first test, if they make B's the rest of the way, they'll end up with a B in the class. And if they make A's the rest of the way, they'll make an A in the class. So you can still make any grade you want at the end of the semester, but you've got to keep up with your WebAssign homework and meet the due dates. And if you do have a poor test grade, it means that your final exam, that you do need to pass the final, certainly. So anybody have any questions?
No.
All right.
I'm good.
All right. Remember, I have online office.
Question, I'm sorry.
Okay, Michelle.
Okay, so I remember you saying, so if we do the odd, if we need to check our words to see if we're doing it right, we can't check in the back of the book?
Yeah, so all the odd answers are in the back of the book. That is correct.
Okay. And it's the which book again? I'm sorry.
Well, I've given you the link to download the book on my. It's an OpenStax textbook. It's OpenStax Elementary Algebra, and the web link is on my Google site. But it's OpenStax and it's Elementary Algebra. We do use the Intermediate Algebra book also later in the semester, but right now it's just Elementary Algebra is what we're using. And you can download that. It's a free download. And remember, you have access to it through WebAssign also, but the WebAssign version of it, the problem numbers and the page numbers are not the same. So you want to download the book off the web and to get the page numbers and the problem numbers correct. So, all right, if there's nothing else, then everyone have a wonderful day. I have office hours later this evening.